Today we are going to talk about the phenomenon of thermal expansion of bodies. Well, by the basic name, it is clear that we will talk about the fact that bodies, when they receive a certain amount of heat, begin to expand, that is, increase in size. Why does this happen? Let's try to understand. Let's look at an object that has some initial length. Let's denote it as L0. It is clear that this object consists of certain molecules, atoms. If this object is a solid, for example, let's say it's iron, then in this case the atoms are in a certain order, which is called the crystal lattice. Let's symbolically label a number of elements of this crystal lattice. And there is a certain structure, that is, these atoms are separated from each other by a certain distance, make certain oscillatory movements about their equilibrium positions. But it's this structure that allows this object to retain its shape and volume at given temperatures. But what happens when we start to heat this object? That is, we increase the temperature of this object, and what does it lead to? As we know, temperature is closely related to how intensively molecules move inside a body. So what happens is that when we start to increase the temperature, the intensity of these particles starts to increase. And what that tells us is that by increasing the intensity of that motion, the distance between the two neighboring layers, so we can now show that conventionally it was the first layer, now the distance between them is bigger. So here we had temperature T1, here we had temperature T2. And thus this expansion begins to lead to the fact that the size of this object begins to increase. And this is characteristic not only for solids, but also for liquids, for gases too. So in this case, in order to describe this process of expansion, we have to realize that there's a definite relationship between how much the temperature of this object has changed and how much its length has changed. In this case, that relationship is going to be directly proportional, so there's a definite increase in length. Let's denote it as dl. And there is a certain increase in temperature. Therefore, let's write down that in order to calculate how much the length of a given object has changed, we must realize that there's going to be a direct relationship to the change in temperature. But it's also clear that you need a certain proportionality factor. For now, let's put it this way. What does this coefficient depend on? It is clear that this coefficient will depend on how long this object is initially and source, what material it is made of. Different substances have different coefficients of expansion because the arrangement of atoms is different. The atoms themselves are different, and each substance reacts differently to increases or decreases in temperature. So in order to understand how big a given expansion will be, we have to introduce a certain coefficient that will show this dependence. And now, in order to properly calculate the relationship between the initial length and the final length of a given object, we need to see how much the length of the object changes if we, say, double its length. If, say, we have an increase in the length of the object with the value L0 of dl, what happens if, for example, we have an object of length 2L0? That is, how much will it grow in length when heated by the same dt? Well, here it's obvious that the increase will also be twofold, because we can conditionally divide this object into two parts. Each of them will have a length L0, and accordingly, each of them, when heated, will give an increase in dl. Let's show it now in the figure like this. So, relative to its first length, this part has increased by L0 and dl, and here respectively the second part has also increased by the same amount, L0 plus dl. Thus, it turns out that the total increase is 2 dl. Therefore, it turns out that the change of length will depend not only on what this object is made of, but also on what length it had originally. So you and I can now get a formula that will show us the dependence of the change in a given length, primarily on how long the object was at the beginning. Then we need to know the coefficient of expansion. So this will be, again, a tabular parameter that determines the value directly. By how many % this expansion will occur? Well, and accordingly, delta T, that is how much the temperature itself has changed. So knowing these parameters, we can determine by how much the increase or decrease the value in the length of the object. Moreover, I pay attention to the fact that dt here can be both with a plus sign and with a minus sign. So this formula will work in both directions and at expansion and contraction of this object. Where can we encounter this phenomenon? Well, first of all, let's remember the fact that the same thermometer that we've been talking about, that is a temperature measuring device, is liquid. It's based on the effect of thermal expansion. So when we have thermometer and we look at its reading, we tend to fix the temperature value by the level of the liquid where it stops. In this case, at a given temperature, the liquid has a certain volume. If the temperature starts to rise, then the liquid level starts to go up as well. And at a new temperature, it will move to a new position. This is an indication that the liquid in this vessel, it has become larger in volume, so its level starts to rise upwards. When accordingly the temperature drops, the level of the liquid will automatically go down. Thus, according to the change in temperature, the level of the given liquid will also move. Therefore, the liquid thermometer works exactly on the effect of thermal expansion or contraction of liquids. If we look around in the same way, you and I can see that the building is constructed from different materials. In particular, the most common ones are iron and concrete. Why exactly these materials were taken as a basis? Not just because iron is plentiful, but because iron and concrete are found to have the same coefficient of thermal expansion. That is, they have the same parameters. So when the building is cooled or heated, these substances begin to expand or contract in the same way, which does not lead to excessive stresses inside the walls. Otherwise, if iron, for example, were to expand faster than concrete, it would cause additional stress and quite possibly collapse the structure. On the other hand, you and I can also see that when a railroad is built, there are certain joints, gaps between the two rails. Again, this is done in order to account for the expansion of these rails in hot temperatures, and so that the streetcar or railroad tracks do not start to deform. So there is a certain amount of clearance for the expansion of these objects. And looking around you, you can see many such phenomena where we can meet the process of expansion or contraction of objects when their temperature changes. And that's it. I've traveled with you. See you in our next lessons, where we will apply this knowledge in practice. Bye, everybody.